Hey Boris, so I'm noticing that there's a common misconception that you're kind of making about the multiplication rule in general and applying it to the OR rule, the addition rule a lot. So I just wanted to make a quick video just to kind of explain this because I think it's easier than me having to type out the whole thing. So first, I know you understand this concept of whenever we're trying to find the probability of A and B, of two events happening, both of them, then we can just multiply the probability of the first one times the probability of the second one. However, if you notice the AND rule, the general AND rule, or multiplication rule, it's actually this right here, where we have to multiply by the probability of the second event given that the first one happened. So there is that special case, though, where if two events are independent, then we can just multiply the two probabilities straight out without having to worry about the conditional probability. And if you kind of think of where this happens, why we have this for independence, well, what does it mean to be independent is that if we want to find the probability of one event and we know the outcome of another, well, they're independent if the second event really doesn't affect the first one, or the first one doesn't affect the second one. So when I have this probability of B given A, this is basically saying what's the probability of B given we know something about A already. Well, if knowing A has no effect, when really we can just completely ignore that. So being independent, the way I like to think about it is this definition here. So I have the probability of B given A is equal to the probability of B. So this is my definition of independence. So the reason why I like this one, because it's more intuitive to me, because it's just like saying, what's the probability of B if I know this outcome from A? Well, it doesn't matter what happened with A, it's the same thing. It's still just the probability that B is going to happen. So now you can see in the second formula, when we're looking at just independent events, if I want to find the probability of A and B, well, it's just going to be the probability of A times the probability of B given A, which doesn't matter, so it's just the probability of B. So this, again, we can only use if we know they are independent, only if we know they're independent. So now going over to the OR formula, which you were using a lot, we have this one where it's the probability of A plus the probability of B minus the probability of A and B. And I noticed in your answer key that you're using this right here. You were calculating this a lot using this formula, the independence one. Oops. Probability of A and B. But again, we can't use that formula for A and B unless we know they're independent, which is not the case in a lot of the problems. So let's take a look at some of the ones that you were doing here, and then we'll redo them. So for number 8, I know this is the first one that I saw that you came across it here. It says, find the probability that a randomly chosen student on the trip was either from Santa Fe High School or at the History Museum. So here, you were using the correct formula of the probability of that we want to go to Santa Fe plus the probability of going to History Museum minus the probability of both. So, and you did the first part correct where we have, okay, well, the probability that a student randomly selected goes to Santa Fe is 50 out of 191, plus the probability that a student goes to the History Museum is 45 minus, or over 191. But here, then, when we're trying to find the probability of Santa Fe and going to a History Museum, well, they're not necessarily independent. So what you did right here, where you're subtracting out when you're subtracting out their product, we can't necessarily do that because, again, we don't know that they're independent. So we just have to be able to find what is the probability of Santa Fe and history both happening at the same time, and we can get that straight from the table. It's these students right here. Right? It's just those 18 are the only ones that are attending Santa Fe High School and going to the History Museum. So that's what we need to subtract out. So it's the probability of A plus the probability of B minus their intersection, the ones that are both, which is the 18 out of 191. And then this will give you the correct answer. So then you have the 95 minus 18 is 77, I think. I don't know. Right, so if you take that 77 out of 191, well, that should be approximately 40.3% or 0.40. And this would be the correct answer for that one. For letter B, it says find the probability that a randomly chosen student was either from Santa Fe or at the art museum. So you would do the same thing. You would have to take the probability of Santa Fe plus the probability of art minus their intersection, which again would just be, it's hard to see my mouse here, only these people here. So if we would do that, same thing, just set it up the same way. So you have the 50 out of 191 for the Santa Fe. This time we have art, which is the 55, and then minus the 15. That's 90. And so if you take that one out of 191, that's about 0.47. And that's the answer for part B. So now let's go to the question that you were actually asking about, which is number 16, I think. I think I put it in here. Let's adjust it. All right, so part A, part B, those are both correct. So let's just look at part C, because you're making that same mistake that I was talking about. Is you're adding two probabilities and then you're subtracting out their intersection, which you can't do this unless they're independent. And not only that, but this 10% and this 20%, those are not the probabilities of getting hurt. Those are the conditional probabilities of getting hurt. So we kind of have to think of this a little bit differently. So the question is asking, what is the probability that he gets hurt this weekend? Well, how is he going to possibly get hurt is if he goes surfing and gets hurt, or if he goes diving and he gets hurt. So basically, that's what we're thinking about. We have to think, okay, there's two ways that he can get hurt. It's going surfing and getting hurt, or he's going diving and gets hurt. Right, so we have this first probability. Oops. We have that first probability and the second one. So you were thinking the right thing of we're using the addition rule here because we have this or of two separate probabilities. But the thing is, we actually don't even need to subtract anything out, because what's the probability that both are going to happen is 0. These are disjoint events. He's only going to go surfing or he's going to go diving, but he's not going to do both. So we don't have to worry about both of those things happening. He can't get hurt for doing both. So really, this is just the addition rule, where we just have to add the two things separately. So where's my mouse now? So this is the same thing as what's the probability that he's going to go surfing and getting hurt, plus the probability that he's going to go diving and getting hurt. And your tree chart is going to help out a whole lot in this. So we just have to add those two probabilities together, and I'm running out of space here. Let me scroll down. So basically, this question is just asking, what's the probability that he's going to be going down this tree, this tree branch, surfing and getting hurt, or diving and getting hurt, or this tree branch here. So just like you have here, we can find the probability that he's surfing and getting hurt just by multiplying going down the tree branch. So that one would just be the 0.2 times 0.1. And then the second one, diving and getting hurt, that would just be the 0.8 times the 0.2. So this one would just be 0.2 times 0.1 plus the probability that he dives and gets hurt. And again, these are two disjoint branches. He can't go down both of those branches, so we don't have to worry about taking out the intersection. So we just have to add these two probabilities together. So that's what 0.02 plus 0.16, and that gives us 0.18. And so that should be the correct answer on that one. All right, and so just one more I think there was another one that had a mistake too, but I'll just point out the number and the email, and then you can take a look at it. Similar to the first one I did. Oh yeah, this one. The last one where you weren't sure how to talk about if it was independent or dependent. So we have this first, second, third class thing, and it says what is the probability that a passenger hopefully it's a randomly selected passenger did not survive. So that would just be the 817 out of 1317 is what you were talking about. And then letter B says, what is the probability that a passenger did not survive given that he or she is in from the third class? So that's where you did the 528 out of the 709, and you got 74%. So if you remember what I was talking about, what it means to be independent is when we know that one piece of information does not affect the other one. So knowing the outcome of one thing does not affect the other. And I gave this definition earlier. I like to use this one as two things are independent if the probability of A is equal to the probability of A given B. Then A and B are independent. All right? So basically, I'm looking at these two probabilities. This right here is the probability of did not survive. So let's write it in this form, so maybe it'll make sense a little bit. Did not survive. And this one right here is the probability of did not survive also. But this is given that it was third class. So if you see here, this one is like saying the probability of A, the did not survive, the first one. This one's the probability of A, and this second one is the probability of A given some other event B, some outcome from the event B. So, and we see just by the just by the formula or by the definition, those are not equal. 62% is not the same as 74%, so those would not be independent. They're dependent. And the way you can think about it is, okay, the probability of surviving is 62%. And the probability of not surviving, knowing that it's a third class, is now higher. It's 74%. So by knowing this piece of information about the passenger, by knowing this, it affected our probability. Meaning the probability that they survive depends on the probability. So it's not independent. They're dependent. They're dependent events. So again, if they were the same number, then let's just say we were to do this, and we found that let's just say out of the 709, instead of 528 dying, it was 440. So let's just say it was 440 instead. Well, if you found the 440 out of the 709, you would get about 0.62 also. So if it was 440 that died out of the third class passengers, then you might say, oh, they seem to be independent, because knowing that the person was in third class knowing that they're in third class, it did not affect their probability of survival, then they're independent of each other. But in this case, since we got 74%, it changed it. It increased their probability of dying, and so they're dependent events. So in letter C, it says, are these two events independent? Well, you're correct. It says, no, the events are dependent. I guess I should. Right? So I would say, no, the events are dependent, because knowing that the passenger was from third class affected the probability of survival.